Hello, and thank you for taking the time to listen to my talk. My name's Ivan Clayson, and I'm a scientific computing officer based in our scientific computing department at the MRC Lab of Molecular Biology in Cambridge. Today I'm going to be presenting a case study of a major Ceph outage of our backup system we had last summer, and I'm going to go through some of the steps we did and the tools we used to bring our file system back up without any data loss or needing to actually recover the data from some external source. So just to sort of state now and caveat everything, I'm not actually a developer or a professional programmer, so please don't ask me any really hard questions. And sorry if I get a few things sort of misrepresented. Okay, so there we go. So like I said, I'm from the MRC Lab of Molecular Biology, or just LMB for short, where we're a national research institute funded by the public, so UK taxpayer money, that focuses on molecular biology. So this includes various subdisciplines, such as structural biology. So that's looking at the actual structure of proteins and how they interact with stuff. Neurobiology, where we develop in silico brains in what are called connectomic maps to simulate brain function. Genetics and genomics, and many other sort of subdisciplines as well. We produce world-class research, and 12 Nobel Prizes have actually been awarded to work done by scientists at the LMB. So just to give you a sort of idea of the estate we have at the LMB, we use a large amount of on-prem, predominantly GPU and some CPU compute for computational biology. This research requires a significant amount of storage where we use Ceph, and specifically Cephs as our main storage solution. Our Cephs estate consists of 3 user-facing clusters, totaling just over 17 petabytes of data, and a single Cephs cluster that backs all these up. Where I've just put a picture of one of the racks of our backup cluster, sort of on the left here, or I suppose on your right, just sort of help visualize what we got. So our backup cluster, which we've called Pebbles, is a 36-node cluster consisting of 1,608 bay JBOD units attached to 32 bulk data nodes. So that's 2 heads per JBOD and 4 metadata nodes, where 3 of them run our 3 monitors, managers, and metadata server daemons. So our bulk data pool is stored on spinning SAS disks, whilst our metadata is stored on NVMEs. We have 8+2 erasure encoding on our bulk data pool and double replication on our metadata pool. So our backup solution consists of taking snapshots of our user-facing file systems at midnight, and then backing up those snapshots to our backup cluster, where we keep about 30 days worth of snapshots. The big advantage of using snapshots, of course, is that we actually only end up copying data which has been changed rather than backing everything up every day. However, despite only backing up these deltas, we still have about 3 billion objects in our bulk data pool, where many of these objects are stored in a single file system with a single active MDS, where this file system is called Ceph Backup, very creatively, and houses all of our Ceph backups. So we had this backup running for about a year, and then one day I walked in and saw that our backup system was hanging when doing an LS or when you tried to mount it. Now, our Ceph health status says that our file system is degraded and that we don't have any active MDSs. And our single MDS seems to be stuck in this laggy replay state. So normally when an MDS daemon fails for some reason, a standby MDS will briefly enter the replay state as it takes over from this failed MDS. This initial replay state involves reading and ultimately recovering the journal entries for that failed rank. And after going through the failed rank's journal, it then enters the reconnect stage, where it reconnects with any clients which were initially connected to it. And finally, after doing that, it then enters this rejoin phase, which is where it reestablishes locks on the metadata. And if you've got multiple MDSs active, that's when this new standby MDS then rejoins the cluster's metadata cache, which is the cache which is shared between the various ranks on the file system. However, our MDS seems to be stuck in this replay state, and is laggy, which means that it's stopped communicating with all the monitors, so it's probably crashed. Now, if we start any of the other MDSs up again, then this laggy MDS instance will be sort of instantly killed, and the new MDS will then start to try and take over. It will enter this replay state, but it won't ever progress this reconnect state, and it will then just become laggy as well. So this points to something wrong with our journal, since our MDS can actually start entering the replay state. It doesn't immediately fail, but it can't seem to progress for some reason. So if we investigate this further, we can increase the debugging setting on our MDS and follow our MDS log, where if we do, we end up with all of this, where there's a hell of a lot more in your actual log file. So this is pretty dense. There's a lot going on. There's a lot of words and characters, but what does this actually mean? So if we look at the last couple of lines in our output and sort of break it down, we can first see that there's a note about there being an open inode. So we've got a file which is open, and we're doing some I/O on that, where we're probably doing some I/O during this crash. Next, we have a note about our inode table, where an inode table, it just lists all the inodes that you actually have available to allocate. And the rest of this line just says that the current version of the inode table in the journal is the same as the stored one. So they're the same, and that's all equal. After this inode table, we then look at the session map, where this session map is going to be a list of all the client sessions we have. So that's going to list all the file capabilities the clients have, what state they're in, whether or not they've got any pre-allocated inodes, that sort of thing. So the live session map in the journal is one value ahead of the actual stored value. So the journal's got the next version of the session map in it. And finally, we've also got the section which just listed, which just lists all the pre-allocated inodes by the clients. Then we actually have the crash, which is for this interval set function, where the beginning of the offset, so that's that p value there, well, the first member of the p variable, is actually defined as before our start value, causing this assert, which just points out this isn't the case and causes our fatal crash. So bringing this all together, there's probably some sort of corruptional error with our session map in the journal, which may be due to maybe there's some sort of pre-allocated inodes being used which shouldn't be, or there's some sort of confusion around what the clients have or what they're trying to do. But either way, this is causing the replay portion of the journal to crash in some manner. Okay, so we have an idea of what the problem is, and it seems to be an error with our journal where replaying causes our MDS to crash and it can't progress. So if we navigate our way to the disaster recovery page, where I've included the link just at the bottom here, to that, we first got to take notice of this big, bold warning message here. So the tools I'm going to talk about now are very, very dangerous and can destroy everything. So sort of don't use them flippantly, please ask the mailing list or contact someone for doing these because you can destroy everything. And people are very nice on the mailing list. Big shout out to the mailing list. They're very, very helpful. Please ask them. They're great. Okay, so once you've taken notice of that message and you sent your message to the mailing list at the very least, we're first going to take a backup of that journal. So if anything goes wrong, we can go back. So we'll be using the CephBest journal tool for this, where this tool will act on a specific rank of your file system. And if you've got multiple MDSs for your file system, then you're going to have to run effectively this journal command for each one of those ranks, because each rank is going to have a subset of that metadata load. So in order to do that, you're going to have this -- rank option where it's got syntax of file system : rank. So for our system, it's ceph backup : 0. And once you've exported your journal, you're going to end up with this sparse file. So for example, our one claims to be 82 terabytes, but it's sparse, so it's not actually storing that on disk, thankfully. This is probably going to take a bit of time to write if you actually haven't flushed your journal to the backing store for a while. So just bear that in mind. You can also actually import this journal using this journal import command, which is quite good if you've got a test cluster and you want to play around with these tools in a sort of safe way. Just double check you won't do anything too destructive. Okay, now that we've got our journal back up, we can start doing some recovery work. where the first thing is to try and recover as much of the journal as possible. We can do this by running this recover entries command, where this will go through all of our journal transactions and then try and commit them to our metadata backing store. This is going to skip regions of your journal which are damaged or missing. So even though we've got a corrupt journal, this tool will still work, and it will just skip those corrupted regions. And also this will update our inode table for us as well, so we won't end up with any inconsistencies between our new metadata updates and the actual bulk data pool. Okay, so now that we've recovered as much of the journal as possible, we can then just discard it because we've already saved what we could. There's sort of no hope for it now, so we're going to get rid of it, and we're going to do it with this journal reset command. So now that we're ready to actually start running the recovery procedure, we could run this on the actual metadata pool as it is, but as these tools are quite dangerous, and if you do something, you could cause just further damage to your pool, I'm going to instead build a second metadata pool that relates to the same bulk data pool, but then do all of my recovery on this second recovery pool. So first, we're just going to make sure everything is down and failed, because we can't have our bulk pool edited in any way whilst we do this recovery. So we're going to be overlaying our metadata when we do this, which can be very dangerous if you change your metadata, particularly when you're trying to do the recovery, because we're going to rely on the metadata within our bulk pool. We're then going to need to reset our various tables for the file system, as well as the journal, so that we can start our metadata rebuilding from scratch. Okay, so following this, we need to then actually start rebuilding this metadata itself, where we're going to rebuild this from the bulk data pool using the actual metadata that's stored in effectively the header objects in that bulk pool. And in order to do this, we're going to use this CFS on the run, but I am not. Oh, I think I'll go back a bit. Oh, there we are. So in order to do that, we're going to use the CFS data scan tool, where this has four key commands on it. It's got init, where this is going to write the root inode, where this force init flag is going to be needed, since we're going to be overwriting our root inode, even if we've got any, even though we've got data there. Then you've got scan extents, which we need to run, and this is going to scan all the objects in our file system to determine the sort of last modified time, various other timestamp information, as well as their sizes. Then there's scan inodes, where this is going to look at the first object of every file. So whilst each inode is going to have one object, each file might actually be spread over multiple objects if you've got quite a big file, before we sort of consider redundancy. So we're only going to be looking at the first object, which we pull the metadata from using the scan inodes command. And then finally, we've got this scan links, which will look at our inode linkages and fix them if there's any problems with them. So these middle two scans examine our file system most intensely, as well as our object pools most intensely. So if you've got a reasonable amount of data in these pools, then you're going to need to run these scans in parallel in order for your actual rebuild process to be done in a reasonable amount of time. Okay. So you can run these scan extents and scan inodes using a task farming approach, where this can be conceptualized in a sort of for loop structure, like I put up here, where you can just run them as completely independent parallel tasks. I've just done a toy example here, just putting them in a screen session. But you can put them in tmux or just put them in the background. Doesn't really matter how you do it. They're all independent tasks which won't communicate with each other. Okay, so once this process is finished, which will take a long time, we can then think about actually getting this recovery file system back up and running. So the docs recommend running another recovered entries actually on the journal, but the sort of way I've laid out the recovery actually in this presentation, you technically wouldn't probably need to, but recovered entries isn't dangerous in any way, so you can run it as many times as you want and it won't ever cause any issues. So you might as well run it more times than you need, then not enough. There's also these two MDS config options that the newer version of the documentation recommend you disable before going forward. We didn't actually run these config removal commands, but if we're doing it today, it's best to follow the documentation, so we would do that. And these parameters just stop the MDS from looking at all the file and object statistics and rebuilding them when we first start it up. But we didn't have any issues when we didn't remove them, so it's probably not terribly awful if you didn't remove them. Okay, now that we have the metadata populated for our recovery file system, we can let our MDS join this file system. So it's very important to not let the clients join yet, as we'll need our clients. Hello. Either way, because we need to run the scrub at the root of the file system, where we can do this to just clean up and repair any of our recursive statistics. So once you've got this recovery file system up and running and you're happy with the contents, you can then go ahead and remove the old file system and pool, because we can't ever have them ever running again once you've got this up and running. Cool. What are you doing? So no, things broken there. Okay, so this is the sort of formal recovery procedure I've just walked you through. Where this is all fine. Sorry about that, my thing just crashed for some reason. Okay, sorry about that, 1 second everyone. So this is a relatively robust procedure, and it's all fine doing it this way. But the only problem is that this does take quite a while to actually run. So for our example, this actually took about a month to run, which is not really great because we actually only keep backups for about a month. So it's not really feasible going forward. Just 1 second, everyone. Let me just get my speaker notes back. Oh, sorry about that. So actually, when we recovered this was actually out of date by the time this actually had all finished. So all of our data, which we just recovered, we actually then just ended up deleting. So it's not really great if you go through this effort and you've got to sort of delete it anyway. And for us, not having a backup for about a month wasn't really viable and isn't really acceptable. So the sort of trade-off between either recovering and it takes forever, or you just don't even bother recover at all, isn't really great or really viable for most systems. But from the way I just described the backup procedure, is there actually any way which we can do this, but not have to basically take forever doing so? So I would argue yes. And about a month actually after we had this error, we actually got another terrible error, which was actually very, very similar to the one we had in July. So the one I just walked you through was the one in July, and then we got effectively the same error again in October, so just a few months later, where the errors are effectively the same. So if we do our sort of analysis of this and think about this in terms of how we thought about our July log, so we know that we've got a corrupt journal where it's probably an issue with our session map, but the underlying metadata pool is probably fine. And if there are any journal transactions which aren't recoverable, they haven't actually meaningfully altered the metadata pool itself, and we can recover most of those transactions. So rather than actually recovering the entire file system like we did before, we actually are just going to reset some of the file system tables and then try and let the MDS replay as normal, and then just discard the journal and see if we can get our file system up and running. So just as before, we're going to back up our journal, but I'm also going to make a copy of our pool at the Rados level using this Rados export command. So even if this goes wrong, we can go back to our backup of the actual pool itself. Okay, so now that we've got a safe backup of our actual CEFS and all our pools before we try our recovery, we can now then try and recover what we can from the journal using our recovered entries and then once that's done, discard the rest of the journal. So now, rather than rebuilding the entire metadata pool, we're going to just reset the session map, where if we had this error again, I probably would think about resetting other tables. But when I did this last year, we only resetted the session map, and this worked all fine, because my hypothesis was that this was an issue with the client sessions, so this is the only thing which needed to be reset. After we've done that, I then just rescanned all the inode links just to make sure that the bulk and metadata pools were consistent. And notice that I've skipped the very, very time-intensive scan extents and scan inode sections, because these are the parts which took a very long time. And my hypothesis was that the actual underlying metadata pool itself was fine and there's no corruption there. So once we've finished our link scan, I'm then going to run this repair scrub on the root of the file system, where once that's finished, we can do our read-write tests to check that we can read and modify the file system, where this was successful, so yay. And then we can bring it all up for use again. So just to summarize this approach, this is the sort of exhausted formal way of doing it. And that's the first example I walked you through. And then it was this alternative and quicker recovery in gold, which we did in October, where we only resetted the client sessions and actually skipped out the very slow portions of the recovery. And that was successful in our case because it seemed to be only an issue with some of the client sessions in our journal. So just some words of caution about the recovery we did. Firstly, we assumed that our metadata pool was fine and that no transactions actually associated with the corrupt parts of the journal which we couldn't recover had any meaningful impact and alteration to that metadata pool. So if we ignored those irrecoverable regions, that wouldn't cause there to be any actual issues with our metadata pool. So also, we thought that even if there were a couple of objects which were corrupted, that's not necessarily going to be a big deal because we're going to be running a backup that evening. So if there are a few corrupted objects, they'll probably just get overwritten that evening. So the risk of there being damaged backups, that only being a small subset of all of our backups, was considered to be a lower risk than not having any backups really available for the next month. So for us, this quicker approach worked, but your situation may be different. You know, it might not be appropriate for your system. So it's one of those things where you sort of probably do have to have a sit down, a think, and decide your plan of action before really going ahead. Okay, so just before I wrap up, I just want to sort of think about why we had these problems. And our hypothesis was that asynchronous writes with our quite aggressive parallelized R-clone jobs were causing these issues. Where we've actually removed this asynchronous write options. So all of our writes for both our backup and live file systems are synchronous, where we've not noticed a significant decrease in our actual throughput in any way. And particularly for our backups, these are all done within the 24-hour window we give them anyway, so we don't need to potentially increase the actual throughput for that. Also, this was all on Reef, so we've actually moved to Squid now, and this might actually all be resolved in Squid. This might have just been a weird edge case in Reef. That's all fixed now, but we haven't actually tested going back to the synchronous writes, so we don't really know. Okay, so I just want to acknowledge the help of my colleagues at the L&B, as working on all this and all the thinking time you put into this was very much a team effort. So I want to thank them ever so much for that. And a big thank you to you guys for listening to me talk. I hope you found it interesting. And feel free to ask me questions later or just email me if you want.